So this is going to be a bit of a blog about this crazy idea of using burning sodium in the air to give sodium hydroxide as a way of countering global warming. And this, of course, has two nice things going for it. The first one, of course, is this will absorb carbon dioxide from the atmosphere to give sodium carbonate. So burning sodium actually pulls carbon dioxide out of the atmosphere. Now, there's a sort of linearity to this that there's, basically carbon dioxide will pull, you'll need a bit of water in there as well. But actually, no, you don't. It all comes directly from there. Anyway, right. So you need to burn two sodiums to pull a carbon dioxide out of the atmosphere. So you would have to burn megatons of sodium to do this. But the second advantage that you get is when you do burn this, you get this incredible fine aerosol, which is wonderfully hygroscopic. And that's maybe interesting that if you take a look at the planet, and this is going to represent all of the energy that we get from the sun, global warming, all of global warming is an increase in that total absorbance, net absorbance, not of 1 part in 100, but 1 part in 1,000. So basically, if you can reflect 1 part in 1,000 more into space, then basically done deal. So the thought occurs that, if you've got your engines chuntering away and they're actually producing loads of this stuff, which is producing hygroscopic aerosols, this is maybe interesting. So you've got two levels to this. You can either use it directly as a fuel or as a hybrid fuel, burning this along with hydrocarbon as a sort of hybrid fuel, or just as an additive to basically create aerosols. And this has legion problems with it. The first one, of course, being is that sodium is pretty remarkably evil stuff. It explodes in water, catches fire if you get it too hot in the air. But then again, this is kind of what we're after here. So the problem, question one is, how are we actually going to burn our sodium? Now, sodium, of course, is a solid at room temperature, just a sort of little block of stuff, but it melts really quite low, melts at about 100 degrees Celsius. Now, this is actually fairly useful because all engines, ballpark numbers, if this is all the energy you get off burning your gasoline, your octane, 2/3 of it is just waste heat. You don't do anything with it. The bit that you turn in, this is the Carnot cycle. They're fairly robust numbers. With typical compressions that you get in a car engine, you get about 30% efficiency out of them. So, you've got loads of waste heat that comes off a car engine. So, melting, or any engine for that matter. So melting the sodium is not even slightly a problem for this. So what would we do with our melted sodium? Well, it behaves very much like any other liquid. So to burn it, we need to nebulize it somehow. So, car engines do this. You sort of spray your fuel in as a bit of an aerosol. Then you sort of compress it, light it, that's how you sort of harvest the heat out of it. But nebulizing stuff like this is a bit of a problem in that the surface tension of sodium is quite high. Water has a peculiarly large surface tension. A number that springs to mind is about 100. The metals typically are much higher. Mercury is about 400. I forgot what the units on this are, but the liquid metals, things like sodium, I think they're about 200. So they're lower surface tension than mercury, but higher than water. And gasoline and the such like, they're lower down here, I would guess. I don't know, half of that of water or something. Let's go for 30. 30 sounds about right. Anyway, so, when you're spraying your gasoline into your engine, that's about where you're at. So, nebulizing stuff with higher surface tension might be trickier. So, you got two choices. You can either just get your solid, your molten sodium, which has to be up over 100 degrees, and of course, all of your tube going up to your sprayer has to be over 100 degrees. This obviously means they've got to be heated. Tricky, but not impossible. And then, of course, you're going to get your spray, and you've got to get your droplets about the right size for good, complete combustion. That's one way of doing it. But obviously, these things are now critical on nozzle size. And yeah, so I've started ordering loads of stuff that make aerosols. With they're basically all related to things that you would usually spray water out of, and I'm hoping that I can actually adapt them to burn sodium. So the two most obvious ones are, there's the high pressure washers, which, these things will go up to 100 bar, and they have a variety of spray nozzles on them in varieties of angles. Obviously, I don't want to. If I can do this with small scale stuff is better on every single conceivable front. Let's start off on the new one. So, small. What's small got going in its favor? First of all, it's safe, right? If you're only going to burn 20 milliliters or something, there's a limit to what can go wrong. I mean, this is like, setting fire to a firelighter or something. By the way, energy density of gas is about 20 times that of 20 times. No, it's not that much. Three times that of sodium. So, if you worry about the absolute total energies, gas is much more dangerous than sodium. But sodium fires have all sorts of problems of their own that they're fairly difficult to put out, and all sorts of other stuff. Anyway, so the practical upshot is, if I'm going to try and work out how to do this, I want to do it on relatively small scales. So obviously, also there's cost elements to this as well. The cost of 20 grams of sodium is like, meh, who cares? If you're doing it on liters at a time, everything becomes a chemical engineering problem at that point. In the just getting it all to the right temperature, all of this becomes a complete pain. I mean, obviously you've got to do it at some point, but at the moment I'm just after proof of concept experiments. So yeah, I ideally want to keep it to these sorts of things that I can almost do inside. By the way, burning 20 mils of sodium it's about, the density of sodium is about the density of water. So it's about 1 gram per milliliter, which is also a cubic centimeter. So if I burn that, it will create about 2 grams. 2 grams? Yeah, it's roughly 1 to 1. It'll create about 2 grams of sodium hydroxide. So burning 20 grams here will create 40 grams of essentially drain cleaner. Apart from that, as a noxious gas, or it's not a gas so much, it's a fine aerosol. And of course, this will also make some hydrogen. So there's a couple of things that you've got to get right here. You've got to get your burn compositions right. So there will be a first question: can you actually create a nice aerosol with this? The second is, can you actually get the mix with oxygen or air, the oxygen in the air, such that you actually get a really good reproducible burn off of this? Now, that's obviously all going to be a gargantuan pain in the arse. Let's see if this will give me a nice... Good, excellent. Gives me a new one. So what I'm going to do in the first instance is I'm going to make one of these things that just works with gasoline. So I just want a nice spray of gasoline that will actually create a stable flame. Let's see if we can actually get something that looks sort of flamey off this. So I want that to burn, and it's going to burn out here somewhere. And the reason I want to do that is, first of all, you've like I was saying, you've got to get the particle sizes roughly right, and you've got to get the fuel air mix about right. So there are various ways you can do this. The first one is, of course, you use a nice tube like this, and you supply a pressure to it that forces the liquid out, forces it out. The other way that you can do it, which is used fairly commonly, is you have a pipe, but you don't really bother so much with the nozzle, maybe a little bit. But on the outside of that, you pump a higher volume of gas down the outside. So this is just air going down the outside, and you've got your liquid coming down the middle. So what happens here is it's the gas flow around the outside that actually aerosolizes the particles. And again, getting the flow rates on this right will be tricky. And if I can get it right with just gasoline, the next stage gets trickier. So you've got various options. The one that I think I'm tempted to do is if you just get a beaker, sodium is typically stored under oil. Doesn't really matter what. Oil, gasoline's all more or less the same stuff. So something that I happen to know is, through my extensive handling of sodium, is that if you melt sodium and then shake it vigorously, this actually sort of smashes it all up into gazillions of small particles. So you get almost an emulsion of sodium. So the thought occurs that in the first instance, you just establish your flamethrower like this. And in the second case, because it requires no heating, is you then just swap it over from burning gasoline to burning an emulsion of gasoline and sodium. And this was actually, if you'll remember the original video, getting close to what I was after, which is basically you take methane, it's basically gasoline, and let's see if we can do this. Burn it with some oxygen, and you're going to get water and carbon dioxide. So I think you need 1, 2. You need 2 oxygens to do that, and that's going to create 2 waters, carbon dioxide. And then you're going to take your sodium and these 2 waters. So this is now the exhaust flame from the methane. Right? This is all basically going to happen here. You mix up all the gases, it'll burn to form the lowest energy form, and it'll release a load of heat. And like I was saying, one of the things I'm most interested in is characterizing the residual that comes out here. So you take your 2 sodiums plus your 2 waters. That gives you 2 sodium hydroxides. Do that properly. 2 sodium hydroxides and a hydrogen. The hydrogen you also burn, and then you take your carbon dioxide and your sodium hydroxide, and you get sodium carbonate out at the end. So that's the sort of the magic fuel composition, and that would constitute by mass roughly 2 parts sodium, 1 part gasoline, roughly. Sodium's anyway 23 a piece. Methane, this is methane, so that's 16. So yeah, okay, it's going to be very sodium heavy. I'm not even going to start with that. I'm just going to start with I think gasoline, pumping it in here, and I'm going to start getting an estimate of if you can just sort of mix in some emulsion, essentially, of sodium particles to do that. This works quite well with ultrasound as well, by the way. So, other things that you might do, you get your this stuff, you heat it up to 100 degrees, at which point, yes, you're quite right, the oil will be boiling at that point, but that doesn't matter. You heat this up, you've got 2 choices. You either just stick a condenser on the top here, such that everything that boils up here just condenses and runs down, or the other version is it only boils, but when it's boiling, that means its vapor pressure is 1 atmosphere. So you can actually heat this up to, if you've got the right container. Once you're heating these things under pressure, it does get a bit of a more gnarly option. Yeah, stuff that I would probably keep away from if given a choice. But you can certainly get to the point where you can melt your sodium, and then you stick in an ultrasound machine, and that also, I happen to know, smashes up this into lots of small particles, which is also very good. Third option that you can do, which is more expensive, but if we're doing it on small scales, I don't greatly care, is you take sodium and you mix it in with a little bit of potassium. This is a solid at room temperature. This is a solid at room temperature. You mix the two together, and over a fairly wide range, you get a huge amount of freezing point depression. So the sodium-potassium alloy, its lowest eutectic, I think, is -10 or something. Well, it might be just freezing point, but anyway, you can depress the freezing point by mixing in the potassium. Let's get me a new whatever. Right. So this is roughly what it looks like, if I remember rightly. So this is going to be all sodium over here, all potassium over here. Melting point of sodium is about 100 degrees. 100 degrees C. 100% potassium is, I think, 65 degrees Celsius. And the mixture, going up from all sodium to all potassium, it drops down, and I think it looks like that. And this goes down, if I remember rightly, to 5 degrees Celsius, maybe -5, I can't quite remember. That for certain, this is room temperature. So you can actually have something that is overwhelmingly sodium and have it liquid at room temperature. So at that point, another option here, we're only doing point of conceptual things here at the moment, is you would get your sodium potassium alloy at room temperature in, I don't know, some hexane or octane or something, ultrasound it till it becomes very small particles, and then that's what you feed down here. So where am I at the moment? At the moment, I'm sort of torn between these two methods. The first one is you just need to have a pressurized tube of some sort. So this would be a bottle like that, and it needs a pressure feed going in, and you would have sort of sodium potassium alloy or something like that. And then you have to blow this out through a nozzle, which will be very similar. This is the other thing about the nozzles. They need to be metal. Obviously, all flame temperatures are about 2,000-3,000 degrees Celsius, that sort of thing. So plastic is a bad idea here. So they need to be metal nozzles of one sort or another. But again, getting the particle size on this right, these are going to be obnoxious experiments to do, because if you don't get it right, then you've just sprayed a load of sodium everywhere. Now, the cleanup is fairly simple. Just throw a bucket of water on it. And sodium will, of course, explode in water. But as a general rule, these were the safety parameters that we worked out whilst we were doing lots of stuff with the sodium-potassium alloy explosions, actually doing the work on that, is that anything over about 1/10 of a gram is dangerous. For certain, if you're just on pure sodium, by the time you get up to 1/3 of a gram, this is getting really dangerous, because this stuff can explode frighteningly. With potassium, it's highly variable, right? So with sodium, a lot of the time it won't explode, but when it does explode, it's much more violent. Sodium is, of course, much more cheaper than potassium by orders of magnitude. It's also the only thing that's really practical as a fuel, because there is loads of sodium on the world, mostly in the form of sodium chloride, of course, which you have to electrolyze, and you split it up and you get your sodium off, which you can do stuff with. Your chlorine, I've still not really worked out what's a decent use for megatons of chlorine, but yeah, one thing at a time. Anyway, so that's method one. Is you basically just have a pressure feed blowing sodium out through a nozzle. And once it's all aerosolized and split up like that, the hazard goes way down, because you only get these big explosions if it's all in one big lump. Once it's been spread out, it'll catch fire all the time, which makes it not so fun to deal with if you've got lots of flammable solvents around. But fundamentally, it's spread all over the place. So you throw a bucket of water on it, it's probably fine. But these are committed experiments. These are not the sort of things that you're just going to put together on the fly. And the other way is the kind of way that I had previously. So you're going to have your feed of sodium potassium alloy down a tube, and then you're going to have a jacket around that tube, which you'll inject air into, pressurized air, and it'll be the pressurized air passing the nozzle that basically nebulizes it. And so, both of these you're going to get flame. Hopefully, it's flames are complicated things. So, yeah, this is kind of where I am at the moment. I'm trying to work my way through what's a good way of doing this. And yeah, it takes time. Anyway, so that's where I currently am. So what I'm starting with at the moment is just seeing what gives a nice spray with water. And once I've got something that I think it's got about the right flow rates, so I'm probably, if I can get away with flow rates of, 1 milliliter per second is actually quite a lot. It's a fairly big flame. We're not quite into rocket engines or anything, but in terms of what you can safely get away with, that's quite a large flow rate. 1 milliliter in 10 seconds, I think, would probably be ideal. Oops. For an aim point, let's sort that out. 1 mil in 10 seconds. So that means with a 20 mils, you're up at about, it'll run for about 3 minutes. So that the thing is that a lot of the stuff that you get for nozzles is geared up for watering plants, and they have flow rates where this is their lower limit, which is ferocious for me. They're basically designed for pumping water on the plants. Maybe not the best thing to repurpose for burning sodium, but the thing is they're functioning. They're functioning nozzles, so they've got a lot going for them. So, and obviously, this is one of the reasons why the direct nozzle thing might fail, and I might have to go to something more like this. Not entirely certain yet. Anyway, so that's where I am at the moment. If you enjoyed it, give me... I'm never going to be able to draw a thumbs up. Yeah, give me one of those. Yeah. Oh, my word, my art skills. Anyway, and yeah, wish me luck. Okay, until next time.